This program is brought to you by Stanford University.
All right, let's start by talking about the universe as it appears at different distances from us, and a couple of ways of thinking about it. Different distances also means different times. Here's a way to think about it. First of all, put ourselves at the center, and then we can draw surfaces around us at different distances. Literally now I mean distances, perhaps measured in meters. And we can ask what we see. As long as we don't look too far, then the fact that we're looking backward in time is not very important and doesn't change things very much. The universe 100 years ago was not very different than it is today. The universe a year ago, or whatever, is very little different. So you have to go out an appreciable distance before you discover the universe is aging, or that it is getting younger as you look out. And of course, as it gets younger, it gets denser, meaning to say that early on the universe was denser. As it gets denser, it tends to get hotter. If you look out sufficiently far to the point where the universe was, or where the universe appears to have been about as hot as the surface of the sun, of course, it doesn't look to us, when we actually look up in the sky, that it looks like the surface of the sun. And that's because of the redshift, that all the photons coming from that place where the universe was as hot as the sun, in the process of being transported to us, those photons are redshifted, and they're redshifted by roughly about a factor of 1,000. That effectively means that the temperature that we would see in the sky is about 1,000 times lower, or it appears to be about 1,000 times lower than the actual temperature that where those photons were being emitted from. But if we forget about that redshift and we just fold in the redshift into our calculations and ask how hot the universe was at various places, then there's some place where it becomes as hot, just about as hot as the surface of the sun. That's the place where the universe became opaque. It became opaque because the atoms, particularly the hydrogen atoms, the universe was mainly made out of hydrogen and a bit of helium. The hydrogen was ionized at temperatures higher than about 1,000, a few thousand degrees. And so out beyond some place, there are not atoms, but ions. And ions consist of nuclei, which basically means protons and electrons. So there's lots of protons around and lots of electrons. I'll draw the electrons as crosses, and they're freely moving around. They're not bound to each other. Even if they accidentally got bound to each other, the high temperatures out there would cause collisions, the collisions being collisions between atoms. And also another thing which is out there is photons. Those photons are all around us. But when we go backward in time, those photons have shorter wavelength, and the shorter wavelength means that they're much more energetic. So what's going on out in the surface out here is it's full of high energy, not very high energy photons, but X-rays basically. X-ray photons, and there are more X-ray photons. In fact, most of the particles out there are these X-ray photons by a factor of about 10 to the 8th or something like that. Most of the particles out there are photons. That's also true today. Most of the particles in the universe are photons. But the photons are so low energy today that they're not a significant part of the energy of the universe. But at that time, they were a significant part of the energy of the universe, so it's also full of photons. And if by accident an atom happened to form, you know, an electron happened to get trapped, very shortly it would collide with a photon and get reionized. And so what's out there is mostly ionized gas. And ionized gas, the one thing that it's not is transparent. Ionized gas is an electrical conductor. Electrical conductors respond to electric fields by sloshing back and forth and re-emit radiation, and basically they're opaque. So out beyond some distance here, the universe is opaque. It's opaque to us, and so we can't see anything behind that surface of last scattering. The surface of last scattering is the place like the surface of the sun where you go from opaque to transparent. And it happens reasonably suddenly. Basically when the temperature cools down below the ionization temperature of hydrogen, the universe becomes pretty clear and we can see through it. There's some region here which is hard to see, and then inside it we begin to see galaxies and so forth. I want to go back a little bit further, and of course going back and further is a bit conjectural, and it's conjectural, but we can guess what it's like on the basis of known laws of physics. Laws of physics here that we're talking about are atomic physics. We know all about atomic physics. We know a great deal more than just atomic physics. We know nuclear physics, we know particle physics. We can go a fairly long way out. I don't mean long in distance necessarily, although it is long in distance, but to higher temperatures and pretty well guess what was out there. So let's talk about what was out there. Incidentally, the particles in here, in addition to the photons, are mainly protons and electrons. Now, the protons mean the nuclei of hydrogen. There's also some helium nuclei, alpha particles, and a few deuterons, which are an isotope of helium, but basically just very simple elements like hydrogen and a little bit of helium. As far as nuclei, electrons freely moving around. Now, no antiprotons, no positrons, or practically no antiprotons, practically no positrons, just ordinary matter, pretty much. Ordinary matter except ionized. Now, as we go out, we eventually come to a temperature which is high enough that when two photons collide, there's the wiggly lines represent photons. The two photons collide. Normally you think of photons as not things which collide. You think of ordinary light. Light just passes through light. But high energy photons do collide with each other. And basically what happens is they create electron-positron pairs. What comes out of here could be two photons again. In fact, the photons might not even collide. They might just go right through each other. But with some probability, a probability of about 1 in 10,000 or something like that, these photons can create an electron. Let's call it E minus. The minus stands for the fact that the electron has negative charge, and a positron, which means the antiparticle of an electron. A positron, which we call E plus. Positrons and electrons are very, very similar to each other. They are practically identical with one exception. They have opposite charge. They have the same mass, exactly the same mass, and properties which are almost direct reflections of each other. For example, if you take two positrons, they will behave exactly the same way as two electrons would behave, except with electrons being replaced by positrons and so forth. Almost exactly, not quite. So if you go back far enough, now this will not happen with ordinary light, and the reason that the light in this room, or the colliding light between the two bulbs up there, and the reason is that the photons don't have enough energy. The energy of these two electrons, even if the electrons were standing absolutely at still, if they had no motion at all, the energy would be twice, two because there are two of them, times the mass of the electron times the speed of light squared. Now, that's a significant amount of energy. It's a lot more energy than photons, for example, from the sun. 2 photons from the sun have energies much, much less than that, thousands and thousands of times less than that. So 2 photons colliding, for example, from 2 different stars will not have nearly enough energy to do that. But as the temperature goes up, as the universe gets more and more dense going backward in time, the photons become shorter and shorter wavelength, and eventually, out somewheres or at some very early time, the universe was hot enough that photons, when they collide, make electron-positron pairs. Electron-positrons can collide with each other and make photons. Exactly the inverse reaction can happen. If you were to take a pot of material at that temperature, you would have reactions similar to chemical reactions, except the chemicals now would be replaced by particles, and the nature of the chemical reactions would be photon pairs become electron-positron pairs, electron-positron pairs can collide. In fact, this positron over here can collide with some other electron over here, make more photons, and eventually if the pot is allowed to just sit there for a long enough time, it will come to a thermal equilibrium. And in that thermal equilibrium, there will be a certain ratio of photons to electrons and positrons. The number of electrons and positrons, you would think, if we really, really started with no electrons and positrons to begin with, now that's of course not accurate, there are electrons in our universe, but in fact the electrons are very, very dilute compared with the photons. There's approximately 10 to the 9th photons in the universe for every electron, so let's ignore the electrons which are there to begin with. But as we go backward, electrons get manufactured by this pair production process, and so that in the early universe, the only way they can be manufactured in this way is to manufacture both a positron and an electron at the same time. So apart from this little bit of excess of electrons that's presently here now, as we go backward, we come to a time when the universe had equal amounts of electrons and positrons, or almost equal amounts of electrons and positrons at some temperature. At first means at temperatures which are not too high, there will be more photons than electrons and positrons. Why is that? Well, if we lower the temperature down below where the photons have enough energy for this, there won't be any electrons and positrons. So it stands to reason if we raise the temperature a little bit, just above the threshold for making a few electrons and positrons, there will be mostly photons with a few electrons and positrons. But as the temperature heats up, and what this has to do with is the fact that the electrons have mass and the photons don't. Photons have no mass, electrons have mass. Electrons have some internal energy due to their mass, photons don't. But as you heat it up higher and higher, the kinetic energy of the electrons becomes much, much larger than their mc squared energy, and the mc squared is not important. So eventually when the temperature gets much above the threshold for creating electron-positron pairs, electrons and positrons, their mass is not important. The photons have no mass. Electrons, positrons, and photons become energetically very similar to each other. And all of a sudden, not all of a sudden, but at that point, the number of electrons and positrons, the density of them, is about the same as the number of photons. Roughly speaking, electrons photons and positrons all have the same density, and they're all colliding around like mad. This is a very, very dense soup of charged particles. But what about the protons? The protons are still present. Incidentally, they're rather dense by now, millions of times denser than they are in this room. They're very dense, the protons, but there is not yet enough thermal energy to be able to create protons and antiprotons, for either photons to collide and create protons and antiprotons, or electrons and positrons to collide. Why not? Well, it's because the energy of a proton is m proton c squared, and that's about 2,000 times larger than the energy than the mass of an electron. The mass of a proton is about 2,000 times larger than an electron. If you wanted to create a proton and an antiproton, you would need at least that much energy. So, as you go back, the universe contracts in the sense of going backward in time. Universe contracts, gets hotter and hotter and hotter, and eventually it rises to the threshold where it becomes hot enough that the particles can create proton-antiproton pairs. And so this dense soup now becomes a soup of photons, electrons, positrons, protons, and antiprotons. But that's not really quite accurate. And the reason that, no, it's not, it's more or less accurate. It's more or less accurate. Incidentally, the number of protons in the universe is as far as we know, is the same as the number of electrons, because the universe is electrically neutral. There's no net charge in the universe. So the universe is electrically neutral. And if it's electrically neutral, it must mean there's as many positively charged particles as negative. The only thing around today are protons and electrons. And so only charged particles around today are electrons and protons. So the number of electrons and the number of protons is the same today. But of course, once these positrons got into the act, there were a lot more electrons and positrons than there were protons. But now we keep heating it up. We keep heating it up. What happens is not that we really create large numbers of protons and antiprotons, but very shortly, by the time we get to the energy needed to create protons and antiprotons, there's also enough energy to smash the protons into quarks. And so, by the time you get to the energy or the temperatures where protons and antiprotons become significant in this soup, really what you have is quarks. 3 quarks for every proton, 3 antiquarks for every antiproton, and basically the kind of reaction that can take place. I'll just draw you some simple diagrams that show you what kind of reactions can take place. The simplest one is an electron and a positron come together, E plus and E minus. They create a photon. That photon very quickly becomes something else. It becomes a quark and an antiquark, Q. That stands for quark. Could be a positively charged quark and a negatively charged quark. There are, in fact, several different kinds of quarks. There are quarks whose charges are 1/3 of the electron charge. There are quarks of charge at 2/3, but I don't want now to get into the particle physics of quarks. The main thing is that the soup becomes a soup not only of electrons, positrons, and protons. The protons are replaced by quarks, and in addition, lots and lots of antiquarks. Almost as many quarks, antiquarks as quarks. And so if we go back far enough, Mesons are made out of quarks. Once the temperature gets high enough to shatter a proton, it also shatters the mesons. Now, there's one more constituent. There are other particles there, too. There are neutrinos and all sorts of particles. Also, gluons. What are gluons? Gluons are very much like photons, but they're the things which are involved in holding quarks together. So there's all kinds of garbage. I mean, it's a hot soup of all of the particles that we normally consider in atomic physics and in nuclear physics. Okay? That's when the temperature gets to be hot enough for protons to be disassociated. If you ask me in degrees how hot that is, I will have to think for a while. Ask me later. We can work it out. But at some temperature, this begins to happen. Now, yeah?
This would be hotter than, say, inside a star.
Yes, this is hotter than inside a star, definitely. Inside a star, there are no anti-particles for the most part, right? So there aren't even positrons of any abundance inside stars, yeah.
So the sequence is going backwards in time, right?
Yeah.
So the real sequence is the other way around.
Yeah, the real sequence is the other way around. That's what. But I want to get to. I want to go back to a starting point and then discuss how it happened. All right. So if you get things hot enough, there's going to be a huge density of particles and antiparticles. The particles and the antiparticles will occur in pairs like this, so there will be an equal abundance, almost essentially an equal abundance of positrons and electrons on the one hand, and almost equal abundance of quarks and antiquarks. In fact, if we go back sufficiently far, then the universe contains more or less equal abundances of every kind of particle and its antiparticle. It starts out, it's electrically neutral, because it's electrically neutral today. Incidentally, there's kind of an interesting reason why the universe is, or a simple way of thinking about the fact that the universe is electrically neutral. If the universe is closed and bounded, in other words, if it has the shape of a sphere, a three-sphere, not a two-sphere, but if it has the shape of a sphere, just think about this for a moment. Let's use as our model of the universe a two-dimensional sphere, the surface of a balloon. Now, electrically charged particles put out lines of force. Those lines of force are the electric field. So if I put an electrically charged particle, let's begin with flat space. Here's flat space. And let's put a positively charged particle in. Electric lines of force go out away from that particle. And those electric lines of force are simply the electric field, or a way of describing or representing the electric field of the charged particle. But it's useful graphically to just think of it as lines of force. And the lines of force neither begin nor end except at charged particles. Okay. What law of physics is involved in saying the lines of force never end except at charged particles? Well, it is Maxwell's equations, but it goes back a little to something a little simpler than Maxwell's equations. It's the Coulomb force, the 1 over r squared force law. The 1 over r squared force law is the rule that says that is equivalent to the rule that says that the lines of force never end except on charged particles. Positive charged particles put out lines of force. Negative charged particles suck in lines of force. Now, that's fine, but supposing we lived in a world which was this closed and bounded spherical world. Supposing we put a charged particle into it. Let's put the charged particle over here. Then the lines of force go out, but they don't have anywhere to escape to. What happens to them?
They just go around forever?
Well, they don't move. I mean, they can't go around. No, they don't go around forever. They simply refocus on the other end of the sphere, on the other pole. Supposing, for example, supposing we put a positively charged particle at the north pole of the sphere. Turn this up so that it's the north pole of the sphere. Then they simply refocus at the south pole of the sphere. I don't know how to draw that. They refocus at the other end of the sphere. But refocusing means that the lines of flux, the lines of force which flow outward from the positive charge over here, necessarily converge at the antipode. And what would that be if this were a positive charge? It would be a negative charge. Right? So in a closed and bounded universe, you can't have a net charge.
If you're saying if there was no negative charge there, there would be one there.
If there was no negative charge there would be that one there. Right. Right. It's just where the lines of flux converge. All right, but really charged particles are charged particles, so you can ask what kind of charged particle would be there. The answer is any kind of particle with the opposite charge. So if this were a proton, this could be an antiproton or it could be an electron. The only rule is that every plus charge has to match, or the number of plus charges and the number of minus charges have to match. In other words, in a closed and bounded universe, the net charge must be 0. Now, it's not clear that we live in a closed and bounded universe, but I just point this out to you as a sort of mnemonic for the fact that the net charge of the universe is 0, or at least it looks to be 0. Any place where we find positive charges, we find negative charges, and we don't find any large-scale concentrations of positive or negative charge. They seem to cancel out pretty well. Okay, so...
Isn't the fact that we can see the CMB evidence of generally transparent space?
Yeah, that's right. I mean, that's right. They can't, yeah. But the charge neutrality is much better than that. The charge neutrality is much better than just the fact that the universe looks pretty transparent. Anyway, it's electrically neutral. That, of course, does not mean that the number of protons is the same as the number of antiprotons. It means the number of protons plus positrons plus all other positively charged particles is the same as the number of the opposite of negatively charged particles. All right, so we started out with a universe with or at least sometime in the remote past, as far back as we can trace, using the known laws of physics, and maybe even going a little bit past the known laws of physics. We come to some stage where the universe was extremely hot. How hot? Hot enough that you name any experiment that's ever been done at a particle accelerator, the universe was hot enough to have had particles in it whose energy was at least that high. All right? That means pretty hot. And at that time, the number of electrons, or the number of electrons and positrons was about the same as each other. The number of quarks and antiquarks were about the same as each other. And there was not only charge neutrality, but now I'm telling you empirical facts. This is not obvious, but I'm going to tell you what the empirical fact is. That, well, there is theory. The theory says that very early in the universe it was hot, and when it was hot, it's hot enough to have an abundance of both particles and antiparticles, because these collisions between photons and other things create particles and antiparticles. All right. Let's suppose that the universe started in a way which was symmetric between particles and antiparticles. Let's suppose it started exactly with the same number of electrons as positrons, the same number of quarks as antiquarks. And in fact, as I said, quarks come in different varieties. So for each variety of quark, let's suppose the numbers were symmetric between particles and antiparticles. The reason that this is an interesting conjecture is because the laws of physics are pretty much symmetrical, not quite, between particles and antiparticles, almost symmetrical. To rather high precision, a positron behaves the same way as an electron does. As I said, I keep saying over and over again, not quite, and it's true that it's not quite. And that's symmetry. That's symmetry between particles and antiparticles, between plus charges and minus charges, has a name. It's called charge conjugation symmetry. It's the interchange of every particle with its antiparticle. Take all particles and replace them by their antiparticles, and that is a symmetry of nature, which I will modify that statement in a little while. But if it were true, you might say, why on earth did the universe not start out with an equal abundance of charged particles of the positive type and the negative type? Or better yet, why didn't it have an equal abundance of quarks and antiquarks? Or did it have an equal abundance of quarks and antiquarks? Let's suppose that it did for a minute. Quarks and antiquarks, in your imagination, you can replace that with protons and antiprotons. Protons and antiprotons are a good stand-in for quarks and antiquarks. So for our purposes right now, we don't really need to think about quarks. We can think about protons and antiprotons. Early on, let's suppose for a minute that the symmetry of nature under reflection replacing particles by antiparticles was actually a symmetry of the universe, that the universe was like that. As many positrons as electrons, as many quarks as or as many protons as antiprotons. And then the universe started to cool. What happened as it started to cool? What would happen as it started to cool? Eventually, it would cool down to the point where the temperature was not hot enough for photons to collide and make protons and antiprotons. It might still be hot enough to make positrons and electrons and positrons, but not hot enough so that when photons or or electrons and positrons collide, not hot enough to be able to provide the large energy necessary to make protons and antiprotons. Then something will begin to happen. The protons and the antiprotons can collide with each other and create photons. The photons have no mass. There's no problem with turning a proton and an antiproton when they collide into photons, but the photons simply don't have enough. Oh, and then of course, a proton and antiproton collide, make some photons. The photons, of course, have enough energy that they could convert back to protons and antiprotons because they have the same energy that they started. The proton and the antiproton become photon to photons. But then the universe expands a little bit. What happens to the photons? The photons lower their energy a little bit because they get stretched. And when the universe is expanded a little bit, all of a sudden those photons no longer have enough energy to be able to create the protons and the antiprotons. So it becomes a sort of one-way street. Protons, antiprotons colliding, making photons. A little bit of expansion sucks the energy out of the photons. Not enough energy to collide and make protons and antiprotons. So there's a one-way flow, sort of. Protons, antiprotons, to photons and electrons and positrons. All right? We start depleting the protons and antiprotons. Then the temperature continues to get lower because of the expansion of the universe. And eventually, it goes down to the temperature where the photons can no longer create electrons and positrons. That's a very high temperature, much, much higher than the interior of the sun, but much, much lower than temperatures associated with protons and antiprotons. And all of a sudden, the same thing happens. Electrons and positrons collide and make photons. The universe expands a little bit. Photon energies are diminished. Not enough energy to recycle back to make electrons and positrons. So the electrons and the positrons start being eliminated in pairs. The expansion of the universe is relatively slow. It's fairly slow compared to the rates of collisions and other microscopic things going on. The universe is a slowly expanding pot of stuff, and it's mostly in equilibrium. It's expanding slow enough that things stay pretty much in thermal equilibrium, except slowly decreasing in temperature. What would happen under those circumstances? What would happen under those circumstances is essentially all of the protons and antiprotons would disappear. They would disappear because they would annihilate. Whenever a proton found an antiproton, they would, and remember, this soup is very, very dense. They would annihilate and form a pair of photons. The electrons and positrons would do the same thing, and eventually all you would have left would be photons. Unless, for some reason, let's say unknown at present, there was a slight excess, or perhaps a large excess, of protons over antiprotons. Supposing that in the beginning, for whatever reason, that protons outnumbered antiprotons 2 to 1. All right? So for every 100 protons, there was only 50 antiprotons. What would happen? Well, the 50 antiprotons would find 50 protons to annihilate with, but there would be no way to get rid of the remaining 50 protons that didn't have partners. So they would stick around. They would stick around and continue to be there, and you couldn't get rid of them. Why can't you get rid of them? Because they can't find partners to annihilate with. Same thing with the electrons and positrons. Since the world is electrically neutral, if it had more protons than antiprotons, it would have to have more electrons than anti-electrons, than positrons to compensate. But exactly the same thing would happen to the electrons. Now there would be, what, 100 electrons for every, for every 100 electrons, there would be 50 positrons. In the end, these things would collide, find each other, and you would be left over with 50 electrons and 50 protons. Okay? Well, that's logic is okay. That logic is fine. But what would happen to the energy of the particles that annihilated? It would become photons. Now, to a good approximation, the way the universe is expanding is called adiabatic. It means slowly. It expands slowly. And for reasons that have to do with thermodynamics, much more with thermodynamics and statistical mechanics than with particle physics, the net number of particles doesn't change very much with time. When an electron and a positron collide to annihilate, they tend to turn into two photons. So as the time goes on, this is really, the really correct statement is that the entropy of the universe doesn't change as long as it's expanding slowly. Slowly means the word is adiabatically. As long as it's expanding slowly, the entropy of the universe doesn't change. But entropy can be translated into number of particles. It's essentially the same thing. So the number of particles doesn't change, which means that the electrons and positrons which annihilated and the protons and antiprotons are annihilated were basically replaced by photons. So the upshot is we can count today how many particles there were at a much, much earlier time by simply counting the number of photons. The number of photons, and remember, almost all particles in the universe are photons. We can count the number of photons, and here's what we find. We find that the number of photons in the universe, well, the number of photons in the universe is about 10 to the 10th, somewhere between 10 to the 10th and 10 to the 9th, times bigger than the number of either electrons or protons. So for every electron and proton in the universe today, there are something like 10 to the 10 photons. That means if we go backward in time to the time when everything was in this hot soup, and there were more or less equal number of every kind of particle and antiparticle, it means that for every proton and antiproton, no, not for every proton, for every 10 to the 9th protons and antiprotons, there was one extra proton. Right? So there was a terribly tiny imbalance between particles and antiparticles that seems to trace back practically to the very beginning of the universe. How do we know that it was such a tiny imbalance? Because we look today and we say all the particles which annihilated turned into photons. So now we look today, how many photons are there for every proton? And the answer is about 10 to the 10th or 10 to the 9th or somewhere in there. That means at early times that the imbalance between particles and antiparticles was only about 1 in a billion, roughly 1 in a billion extra protons for every proton-antiproton pair. Now, it's a good thing that there was that little imbalance, because if there wasn't that little imbalance, there would be no atoms. There would be, everything would have annihilated. Yeah?
Couldn't you look at it slightly differently in the sense that, let's say you started with equal on everything, and statistically you could say the probability of when it cools, that the probability of creating a proton is 10 to the minus 9. Rather than, I mean, you're having these collisions and
Yeah.
as it cools,
Yeah.
you're not
Yeah.
making the collisions anymore.
Yeah, we're coming to that. That's where we're going. Right. You're asking, how do we know that as it cooled that protons weren't made? How do we know that the only thing that happened was annihilation? All right, now I'll come to that. In order for protons to be created in the process, during the process of cooling, as you say, let's suppose there was equal number of protons and antiprotons. Where are those protons go? Where is that extra proton going to come from? We have to create an extra proton. Now, to create an extra proton, in order to keep electrically neutral, we also have to create a electron. So we start out with a world with equal number of electrons and positrons, protons and antiprotons, electrically neutral, but also neutral with respect to particles and antiparticles. And now we want to make an extra proton. So an extra proton, we want some reaction where a proton comes out, but something else has to come out with it because of electric charge, and that would have to be an electron. Or some other negatively charged particle, but for simplicity, let's just say, where did the mass for these come from? Let's say it came from a pair of photons colliding. Well, the only problem with this is the standard rules of elementary particles. The standard model of elementary particles does not contain such a process. It does not contain any process where the net number, now I'm talking about the standard model of particle physics. Standard model of particle physics means standard thing that we know from laboratory physics, and not extensions that may or may not turn out to be correct in the future. The standard model, which describes particle physics very well, up to energies of 1,000 times the mass of a proton contains no processes that involve protons or could create protons that don't at the same time create an antiproton. This is called baryon number conservation. Baryon numbers, for our purposes, is basically the number of protons. You can add in neutrons. Protons and neutrons are very similar to each other. The number of protons and neutrons, protons plus neutrons, minus the number of antiprotons plus antineutrons. That number is conserved in the standard model of particle physics. That means you cannot create a proton without creating an antiproton. And this is not electric charge. This process here is perfectly good for electric charge, one proton and one electron, but it violates one of the rules, empirical rules, entirely empirical, that you can't create a proton without creating an antiproton at the same time. I might add that the same rule, or the same physics, tells you that you can't create an electron without creating a positron. Now, as I said, this is not the conservation of electric charge, because as far as electric charge goes, a proton and an electron together are electrically neutral. It's the conservation of baryon number, conservation of the net number of protons minus antiprotons, and neutrons and antineutrons. So the standard laws of particle physics do not allow, as you cool down, to create an excess of protons. Now, I think that's the question you asked, is it?
Well, I'm not sure.
Well, you asked me how do I know that as it cooled down that the excess didn't develop. And what I'm saying is that the rules of elementary particle physics do not, elementary particle physics up to or down to distance scales 1,000 times or 10,000 times smaller than a proton, do not contain any processes which would allow an imbalance to develop. Okay? Now, what does that really mean? That doesn't mean that in cooling down from some exceedingly high temperature, this imbalance could not have developed spontaneously. What it means is once the temperature gets down low enough to where we know the rules, where the energies of collisions are low enough that we know the rules of particle physics, that there are no processes at those energies, at those temperatures and lower, that can do what you want. But of course, we are always acting to some extent in a sea of ignorance where we don't know what physics is like at yet smaller distances and higher temperatures and higher energies. So one speculation, which is, I would say it's speculative. I would also say there's almost complete consensus among cosmologists, experimental physicists, theoretical physicists, almost everybody, is that in fact the universe did really start neutral. Now, why is it? Why should there be such consensus for something we know nothing about? Hard to answer. Hard to answer. But it does seem a little bit odd. If you go back early enough, you really do want, where did this 1 part in 10 to the 10th come from? That's a very odd thing. 1 part in 10 to the 10th is a very odd thing. It sort of makes you want to believe that perhaps the universe had as many protons as antiprotons to begin with, and as many as electrons as positrons to begin with, and that as you say, that as it cooled, something caused it to be biased in one direction to create a few extra protons and a few extra electrons. That is widely believed, but you have to go back to times and temperatures which were above the temperatures where particle physics has been successfully tested, shall we say, where the Standard Model has been successfully tested. So what does it take? I just want to talk a little bit about your question. What does it take in the way of changes in particle physics, or the way in the rules of particle physics, to allow a universe which started with the number of protons equaling the number of antiprotons? Now, I should say, when I say protons, I mean things with, I mean a collection of objects that includes neutrons, protons, and other objects called baryons. But let's simplify the story to just protons. All right. Let's start, not that a proton equals an antiproton. The bar, incidentally, stands for anti. I don't mean that a proton is the same as an antiproton. That's nonsense. They have opposite charge. I mean that the number of protons, let's call it the number of protons, equal the number of antiprotons. Supposing we start that way in the very, very early universe. Incidentally, these speculations were first made by Andrei Sakharov in the Soviet Union in about 1967. They were totally unknown in the West. Nobody knew about them. And they were rediscovered actually by Dimopoulos and myself around 1980, 13 years later. And the subject is called baryogenesis. Genesis means the birth of, and baryo here stands for baryon number, which means proton number, and so forth. All right, so the idea is, first of all, the laws of particle physics must violate at some level, at some high temperature and at some high energy, it must violate the rule that protons cannot be created without antiprotons. In other words, it must violate a rule called the conservation of baryon number. The conservation of baryon number is basically the conservation of the number of protons minus antiprotons. That's the conservation of that quantity in the Standard Model of particle physics is a known experimental and theoretical fact, the conservation of it. But if you go back to earlier times when the energies were higher, when the distances were smaller, when we go beyond what we really know, there's no reason why this law of conservation of baryons or baryon number must be true. In fact, we believe it's probably not true. There's very, very strong reason to believe a number of grounds that the number of protons minus antiprotons can change. Now, the electric charge cannot change. So that means every time a new proton is created without an antiproton, it must go together with an electron being created. That's okay. We don't mind that. The world is electrically neutral. But the first condition for a theory which starts out with equal abundance of particles and antiparticles, the first condition for it to get shifted a little bit is violation, condition number one, violation of the conservation of baryon number. I'm writing down the three conditions that Sakharov himself wrote down and that Dimopoulos and we discovered independently, and which are generally almost complete consensus about this. That's number one, that the laws of physics must allow processes such as this, where a pair of photons can come together and make a proton and an electron. It would require a new set of interactions, a new set of phenomena, which can only happen at energies so high that we haven't yet seen them in accelerators. So that's number one, violation of the conservation of baryon number. Now, number two, all right, let's suppose there was a violation of the conservation of baryon number. Let me give you an example of a conservation law. Conservation of position, my position. Well, of course, this is not a conservation law, but let's just suppose for a minute it was. That would mean I can't move, all right? My conservation of my location would literally mean I can't move. Now, I could imagine that that's a law of physics, and then I could imagine a small violation of it. A small violation of it would mean I can move a little bit, maybe slowly. But it wouldn't necessarily say that I can only move to the left. That's my left, your right. It might say that I can move a little bit and change my position, but offhand, perhaps equally likely to the left or the right. So a conservation law can be violated, but in a way which doesn't bias either more protons or more antiprotons. It simply allows, in other words, for example, there could be a process in nature like this, and there could be another process in nature, the reflection of it, where all particles are replaced by their antiparticles. This would become antiproton and positron. You might think if this could happen, this could happen. That would mean that the conservation law is violated, but it's not biased in a particular direction. It could increase the number of protons or increase the number of antiprotons, and both kinds of things might be going on. Over here, a proton might be created. Over here, an antiproton might be created. And obviously, on the average, there would be no biasing, and on the average, you would expect, again, that such processes would not lead to a net imbalance of protons and antiprotons. The key is to say, wait a minute, how do I know that nature is truly symmetric or truly invariant under changing every particle to every antiparticle? How do I know that this charge conjugation is really a symmetry of physics, and that everything that can happen with equal probability with particles being replaced by antiparticles? And the answer is, not only do we not know that that's a symmetry, we know that it's not a symmetry. Experimental physics by now has uncovered the fact that there is not an exact symmetry where you replace every particle by antiparticle. That's been known for many years now, that there are slight differences. There are slight, small, residual differences in reaction rates, in probabilities, when you replace particles by antiparticles. That conceivably could bias one of these two relative to the other. For example, this process could have a slightly different probability than this process, this one being perhaps a little more probable, this one a little less probable. Then the bias would be towards protons and electrons rather than positrons and neutrons. All right, that means that we have to also have a violation of charge conjugation symmetry. That there must be a bias in nature which distinguishes particles from antiparticles. Okay. Indeed.
Question?
Yes.
Couldn't it just be that there is a, even if they were unbiased, I mean, that sort of by some kind of random process, just as you approach the point of no return, where you didn't have that reaction anymore, you would have had some excess of one over the other.
Yeah, you might have had some excess of one over the other here, but over here you would have perhaps the opposite excess, and over here you would have.
But still, you might have had an overall excess.
That would, on statistical grounds, you would expect under those circumstances, assuming there was a symmetry, you would expect the excess to be of order the square root of the number of particles. This is usual square root of n statistics. All right? There is something like about 10 to the 80th protons in the universe, square root of n is only 10 to the 40th, and sorry, no, go back. If I take all of the particles in the universe, known universe, there's something like about 10 to the 90th. That includes photons, all right? The square root of that is only 10 to the 45, so that could account for an imbalance of 10 to the 45 protons, but there's more like 10 to the 80th protons in the universe. So it's a very good question. How do I know that it isn't statistical fluctuation, but it's way beyond, yeah, the numbers just don't support that. So that's a very good question. I thought of it myself years ago and dismissed it very quickly. Okay.
Wouldn't it be patchy?
Well, yeah, but you might still expect maybe the patchiness washed itself out, and you know, it's thinkable, but the numbers are too far from that. Now, the last thing is a more subtle thing. There is a symmetry of physics, which is not charge conjugation symmetry, but it's a combination of charge conjugation and time reversal, where if you simultaneously replace every particle by its antiparticle and at the same time run things backward in time, then that is an exact symmetry of nature. You can ask me how we know that. Let me just say that that is very deeply and fundamentally built into the rules of relativistic quantum mechanics, relativistic quantum field theory. I'm not going to try to explain it now. It's called the CPT theorem. You can look it up, the CPT theorem. And unlike the charge conjugation statement, that's a thing which could be wrong. Empirically, it's close to being correct, but doesn't have to be correct. The CPT theorem is a theorem, is a mathematical theorem about relativity and quantum mechanics. And what it says, as I said, is if you take every particle and replace it by its antiparticle, and at the same time run time backward, in other words, take a movie of the universe or a movie of something, run backward, then that's an exact symmetry of nature. Now, if I were to take a pot of hot gas that had been sitting forever and ever and ever for a long time, and it's come to equilibrium and it's just sitting there so that nothing is going in one direction or the other direction, that means a movie of it run backward and forward is exactly the same. It's in equilibrium. But if there's a symmetry that says that if you let time run backward and also interchange particle with antiparticle, but you're in a situation where it doesn't matter whether you run time backward or not because it looks exactly the same, then you have a symmetry between particles and antiparticles. All right? So the last condition in order to break this symmetry between particles and antiparticles is that the universe at some point in its history must have been sufficiently out of equilibrium so that it definitely looked different going one way than in the other way. Now you say, of course the universe looks different going one way than the other way. All right? The universe is expanding, it's not contracting. But on the other hand, throughout most of the life of the universe, it has been expanding so slowly that the expansion was negligible on time scales of elementary particle reactions. Today, the universe expands on scales of 1 billion years. Particle reactions, which are the things which are relevant here, are, 10 to the minus 25 seconds or whatever, very, very rapid. And so the very slow expansion of the universe, you can just think of that as the pot sitting there forever. And for most of the history of the universe, it is expanding very slowly compared to the particle physics rates. Nevertheless, sufficiently early in the universe, the universe was certainly out of equilibrium. Sufficiently early, it explosively expanded. And during that period of time, it looked different from the microscopic point of view, from the individual point of view of particle collisions and so forth. The expansion of the universe was very, very significant, and the universe did not look symmetric going forward and backward. And it's during that time, it's called, the third condition is called being out of equilibrium. Now, it's an interesting theorem that if all of these conditions are satisfied, number one, that baryon number is not conserved, number two, that the symmetry between particles and antiparticles is broken, is not a symmetry, and third, that the universe was for some period out of equilibrium. In other words, that the expansion rate was fast enough to affect particle reactions. Then, even if you start with a universe which is equal number protons and antiprotons, equal number positrons and antipositrons, it will get tilted one way or the other. It's essentially a theorem that, as I said, it was discovered by Sakharov, 1967, and Andrei Sakharov, that is, and is called the theory of baryogenesis. The part of it that we don't know with certainty, this we know, the universe, well, we can conjecture that the universe at the very beginning, at the very earliest times, was, just a second, was expanding rapidly enough that it affected particle collisions. This is very reasonable. This is known to be true. The violation of baryon number is the question mark. We have never seen a reaction in nature where the number of protons minus and when I say protons, I mean protons plus neutrons minus antiprotons minus antineutrons. We have never seen a reaction in nature which violates this here. That may simply be because we've never had enough energy to create reactions that do that. All right, so this is the question mark here. If it turns out that baryon number is not conserved, then it's essentially a theorem that there will be a little bit left over, one sign or the other, protons or antiprotons. When people make models of this and they start calculating, they get numbers not so different than 1 part in a billion. So the 1 part in a billion is not an unreasonable answer, but we simply don't really have a theory that goes back that far. And so at the present time, this is conjectural that the universe started out neutral with respect to this baryon number, and then in the process of cooling, as it went out of equilibrium, as it expanded very rapidly, these other conditions being satisfied tilted it a little bit, 1 part in a billion to protons versus antiprotons, 1 part in a billion to electrons versus positrons. And then in the process of cooling down beyond that, every excess antiproton, every antiproton found a proton, annihilated with it, and only left over this 1 in a billion. Same thing with the electrons and positrons. And today what we have is that tiny fossil remnant of the universe looks like it's very, very grossly matter and not antimatter, but it's a simple remnant of something which was much, much more equal at the early times. So that's an interesting story. Well, Michael had a question.
Yeah, matching up the CPT to the 1, 2, 3 here, I think numbers 2 and 3 are C violation and T.
Okay, let me be more exact. I just call this charge conjugation, where you replace a particle by its antiparticle. It's really something called C times P, where P is called parity and it means spatial.
Two is CP violation.
Yeah, CP violation. Okay. We could call this charge conjugate, CP violation, CP. But it is replacing particles by antiparticles, and at the same time,
Number 3 is T.
say it again.
Reversal.
This?
Yeah,
That's time reversal.
yeah, time reversal.
Yeah, time reversal, right.
Okay, and then number 1 is none of them.
Number one is just something completely different. Now, I should say there's very strong reason to believe that baryon number is not a good, real, genuine conservation law of physics. There are many reasons, but however, it has never been detected, the violation of baryon number. Disappointing fact that, yeah.
How close are we to the Big Bang at this point?
Very close, very close. Well, look, it's a question of definition of what you mean by the Big Bang. There may have been a long period of inflation which preceded what we normally think of as the Big Bang, but what we normally think of as the Big Bang, we're pretty close to the Big Bang, yeah.
Are there estimates for what energy levels you would see the violation of baryon conservation?
Where you would see it significantly, yeah.
And how many orders of magnitude beyond what LHC can do? Is it
13. No, you see, okay, no, it's more complicated than that. All right. Supposing there was some reaction which became important at high temperatures, which really became highly probable at high temperatures, which allowed some collision to take place, which would change the number of protons and so forth. It might nevertheless be, even though you don't have that much energy around, that a process can still happen, but with very, very small probability, extremely small. Now that's typical. That's a typical kind of thing where something can become strong and important when you have a lot of energy, and that doesn't mean that it's impossible at low energy, it just means it becomes very, very improbable. So, if it's true that there are reactions in nature which violate this baryon number, but only significantly with a high probability when the temperature is very high, here would be a process, for example, a proton becoming a positron and a photon. That's a perfectly good. But it might only happen when the proton, let's say, not only happen, it might mostly happen when the proton collides with something else at very high energy that shakes it up a lot and then kicks off this collision. Well, it would still be, in most theories, that it could happen even at low temperature and low energy, but with a very, very diminished probability. How diminished? Well, we know something about the lifetime of a proton. The lifetime of a proton, how long must a proton last? Well, ordinary particle physics reactions happen very fast in terribly small fractions of a second. So just applying ordinary dimensional analysis to this, you might expect that this would happen in a terribly tiny fraction of a second, but it doesn't. It certainly doesn't. Your protons don't disappear spontaneously like that and turn into positrons. How long, what's the minimum lifetime of a proton? Well, I can tell you this, that the proton basically have to last the age of the universe for sure. Okay, for sure they must last the age of the universe because they're still around. So at least 10 billion years. But in fact, the lifetime of a proton is much, much longer than that. The reason is because if the lifetime of the proton was about 10 billion years, then if you took 10 billion protons, which is not very many, then one of them, on the average, would decay in 1 year. If the half-life of the proton was 10 billion years, then in 1 year, if you had 10 billion protons to start with, one of the protons would decay. Now it's easy to see, and then if you had a large number of protons, 10 to the 23rd protons, you would have a lot of reactions of this type taking place. even though the likelihood that any proton decayed would be very, very small. So we know that the lifetime is much, much longer than the age of the universe. In fact, it was known many years ago to be upwards somewhere around more than 10 to the 27 years. It's a very, very long time, much, much longer than the age of the universe. Starting sometime in the late 70s, people started to build very big experiments where they would take very large quantities of material, which usually meant water. In fact, it always meant water. Why water? Because water is transparent and you can look through it and see the light. This, incidentally, would also, this produces a photon, for example. Photons are light. You want transparent materials. Water is good. Take huge quantities of water. Huge means, you know, many, many swimming pools, hundreds of swimming pools, and sit and watch the many, many protons and wait for one proton to decay. Can you see one proton to decay in a big pool of water? Yes, you can. We'll have many, many light detectors. So you have a great big pool of water, photo detectors all along the sides here. And if a proton decays, it emits photons, and you can detect it. So you can detect one reaction in a great big, huge pool of very transparent water. There are all kinds of background noise, so you bury the process deep under the earth in a mine somewhere where cosmic rays, et cetera, et cetera. And it was fully expected that with 10 to the 32 protons, you would see one of them decay in about in a year's time. Nothing happened. So we now know that the lifetime of the proton is longer than something like about 10 to the 34 years. That's a long time for the proton to last. But what we don't know, and what we won't know for many years, is that when collisions happen that really excite the proton, that pump a lot of energy in, that this process doesn't happen very readily. There are many processes in nature, many things in nature, which are very, very improbable unless you have a large energy to excite them. And proton change, or the violation of baryon number, could well be one of those things that it just takes a very high temperature to precipitate. And that's what we don't know. This is still a question mark.
Question?
Yeah.
The baryon conservation describes why, you know, positive baryon, negative anti-baryon, whatever. But since the universe is electrically neutral, what guarantees that there's the same number of protons as electrons?
Well, the basic elementary particle physics processes, for deep mathematical reasons that we don't need to go into here, always conserve the basic processes of nature, such as elementary particle processes, always conserve the electric charge. So roughly speaking, this is a process where the electric charge hops from the proton to the electron, but electric charge can't disappear. So what guarantees it? Maxwell's equations, fundamental symmetries of physics.
No, I mean, like, okay, there's the same number of, in the soup, there's the same number of protons as antiprotons, positrons as electrons.
Right.
But as the universe cooled, you know, the antiparticles disappeared, but the universe is still electrically neutral.
Right.
So
That is what, in fact, happens. Yeah. But it's another question to ask why it got biased towards protons instead of antiprotons.
no, my question is, why is it the same number of electrons and protons? Still electrically neutral. Those
That's because the basic processes of physics, whenever a proton disappears, another charged particle has to reappear. So it can't get out of balance electrically.
Where in this picture does, if we keep rotating the clock back, where do we unfreeze out the photonic degrees of freedom and reabsorb them back?
The which degrees of freedom?
Photonic.
What does it mean to unfreeze photonic degrees of freedom?
Well, if we suppose the photon arises from spontaneous symmetry breakdown of the
Of the standard model. Yeah, that happens at an energy of about 100 GeV, or 200, maybe 250 GeV, it's not that the photon disappears, it's that the weak interactions become much, much more like the electromagnetic interactions. The weak interactions meaning those things involving neutrinos and so forth. So the symmetry breaking, which made the photon special relative to the Z boson and the W boson and so forth, that happened at a temperature about 100 times or 200 times larger than the energy at which protons and antiprotons first were formed in the, but that's known physics. That's known physics. That we know where that happened. And it doesn't, it plays a role, but it doesn't play a dramatic role in this story here. Yeah.
Does dark matter modify this picture in any way?
Not particularly. Dark matter itself, you can ask whether dark matter is anything like, it's not protons, but whether it has its own conservation laws, which had to be broken in similar ways to get a net amount of dark matter. Probably not. The dark matter doesn't influence this particular question in any special way.
It had to be hanging around there.
It was hanging around.
In the very early parts
Right.
of the picture.
Yeah.
Even at very high temperature.
It was there.
Probably.
Right. But in most theories of dark matter, the dark matter doesn't interact very much with ordinary matter, and so it was more or less spectator. Now,
Could it somehow have been involved
it's possible. It's possible.
in the baryon?
It's possible. It's possible, but I don't think it would change the basic principles. Wouldn't change the basic principles. Yeah.
Condition number 3 is equivalent to a violation of CPT symmetry.
No. Well, yes and no. Let's just take T. Forget the CP, just T. T is time reversal symmetry. All right? It means anything that can happen one way can also happen if you ran things the opposite way. But it doesn't say that the actual history of the universe was symmetric. It just says whatever the history of the universe is, if it can go one way, it can also go the other way. All right? Now, all that this says is that the universe was out of equilibrium, which means that it wasn't static, that it wasn't just sitting there like a pot of stew untouched. It was changing. The pot was expanding. A violation of CPT symmetry would mean that running the film backward was not a possible solution of the equations of physics, and that's something. This is. Let's put it this way: to violate this, we would have to violate something very deep about quantum field theory and special relativity and quantum mechanics. So while I don't think any of us can say never that CPT violation is not a possibility. It's not a possibility within the current mathematics of quantum field theory. So this is considered pretty sacred generally. That doesn't mean that the universe isn't going one way. It just means if it's going one way and you run it backward, that's also a possible world, right? Right. For example, I mean, I am right-handed, okay? Does that mean that there's a left-right asymmetry in nature? No, it just means that another creature could exist, doesn't necessarily have to exist, but another creature could exist who was left-handed and be otherwise exactly like me. It doesn't mean that I'm necessarily ambidextrous. It means that whatever I am, the reflection could exist. Same thing about time reversal here. Whatever the universe is doing, it's a consistent set of solutions of equations of the theory to run backward.
with the other changes, the changes in parity.
Yeah, with the other changes simultaneously alongside, that's right. Yeah.
How does gravity affect in all this?
Well, gravity, of course, is deeply connected with the expansion of the universe. But other than that, okay, let me give you let me tell you one of the reasons that we have a fairly strong belief that this conservation of baryon number cannot be an exact conservation law of physics, and it does involve gravity. Before I say that, let me say that the gravitational interactions between particles are so negligible, at least at any reasonable energies, that it really doesn't play much role in this. But there's a logical point which is interesting, and it has to do with black holes of all things. Imagine a black hole being formed out of the material of a star. I forget how many protons and what the baryon number of a star is, but something like about 10 to the 60th, if I remember. Something like about 10 to the 60th protons in a star. It has a net baryon number which is large and positive. Now the star collapses to a black hole. It runs out of fuel, collapses, and becomes a black hole. Well, the black hole may have all of those protons inside it somewheres, but then, at least according to theory, if you wait long enough, the black hole will start to evaporate. It will evaporate into photons, basically photons. The temperature of a large black hole is very, very low, and it's nowhere near enough energy for it to be able to create protons. So this large black hole, which started out as 10 to the 60th protons, contracted, became a black hole, and started to emit ordinary black body radiation. Slowly it heated up, but by the time it heated up enough to be able to create protons, it was as tiny as well, it was a very, very small. Very few protons left to be able to be emitted. So we know from black hole physics and the evaporation of black holes that at some level, the conservation of the number of protons in the world must be violated. That's something that, that most physicists believe. But that's about the only way that I can think that, the two ways that, gravity comes into the story. One is that, that it strongly suggests violation of conservation of baryon number because of this black hole story. The second way that it comes in is it has to do with the expansion of the universe. If it wasn't for gravity and Einstein's equations and so forth, there would be no expansion. And without expansion of the universe, there would be no out of equilibrium. So the expansion of the universe, which is a gravitational phenomenon, is part of the out of equilibrium. But apart from that, gravity doesn't play any significant role in this.
If we had a black hole that was charged, wouldn't that same argument suggest violation of charge?
That's a very good question, but the answer is no. And the reason is because charged black holes, like any other charges, have electric lines of flux coming out of them. And those electric lines of flux are sort of tied down at infinity, and they keep track of the electric charge of the black hole. Electrically charged black holes will not completely evaporate. They will evaporate photons, losing energy, until they get down to some minimum energy called the extremal energy of the extremal black hole, and then they'll just sit there and stop evaporating. And black holes which have stopped evaporating because they have electric charge are called extremal. They're extremal in that they have their mass is the extreme lower end of a charged black hole. So no, charged black holes don't indefinitely evaporate. Yeah.
There's always a confusion when people talk about Big Bang and black hole and the density. If you think of a volume of that great dense soup, you would calculate the radius of a black, that it would collapse into a black hole based on its density and its size. I mean, it's this quark soup that you were talking about is much, I gather, much denser than, say, a neutron star, and the mass is much greater. And
but it's expanding.
so that's
It's expanding.
so because space is expanding.
Well, I don't know. It is expanding because, all right, because space is expanding, or just because it is expanding. No, it doesn't collapse into a black hole. Instead, it does something else. It expands. So, no, there's no issue. There's no issue of all this dense material somehow forming a black hole. That's not an issue. The black hole idea that I just expressed was a thought experiment. It's a thought experiment to try to convince yourself that the laws of physics as we now know them sort of force the issue here, that the conservation of baryon number is not something that will persist indefinitely in physics. By now, there are so many reasons to believe in the violation of baryon number that it's a half a check, at least half a check.
Would one know how to amend the standard model in order to include those reactions?
The trouble is the opposite. Almost any way that you try to amend the standard model winds up making the lifetime of the proton too fast. Yeah. So yeah, it's real easy to make it too much. It's hard to keep it the proton as stable as it is. Right.
Can a proton absorb a photon and reach a higher energy level with the quarks inside of it?
Right, say it again. Can a proton
absorb a photon?
A proton can absorb a photon, and it will get excited. The quarks will start to get excited. We'll get very excited. But of course, the first thing will happen is they'll spit out more quarks, but quarks and antiquarks, mesons. Mesons, maybe they'll vibrate and spit out some mesons. To the best of our knowledge, the amount of energy that you would have to shove into the proton to make it decay and disappear, leaving only a positron, would have to be enormously large simply because the proton is known to be so stable. Known to be so stable, and therefore this must be a very remote and unlikely process. The only way to make it unlikely is to push it to very, very high energy, and so we could talk more about it, but yeah.
Before we discount the question about square root event statistics,
You gotta speak louder.
we talked about square root event statistics before. Square root of n statistics.
Square root of n, yeah.
Right. Earlier, was the number of particles nearly constant, or is it possible that at some early time there were only 10 to...
Yeah. Some of this is theory, some of it is observation, and I'm not going to try to distinguish now, but roughly speaking, the number of particles in the universe did not change from some very early time. The number of particles within a certain coordinate patch, within a coordinate patch. And the correct statement, the exact statement, is that in a universe in equilibrium, or just close to equilibrium, in an adiabatically expanding universe. Adiabatically expanding means that the rate of expansion is much slower than any fundamental particle process or any fundamental process in nature. What did you ask me? I lost track. Yeah. In an adiabatic process, which means a slow process, entropy is conserved. Entropy doesn't change in an adiabatic process. Now, if you take a gas or a soup of elementary particles and you calculate the entropy, it is within a factor of 2 or pi or some numerical number. It's the number of particles. So in an adiabatic process where the universe is expanding slower than particle reactions are taking place, even though particle reactions can take place, and they do take place, and they might even be biased in one direction or another, the net number of particles tends not to change. And if it does change, it changes maybe over the whole history of the universe by a factor of 10 or something like that, not by an enormous amount. So originally, the early questions about the subject had the whole story upside down. Instead of asking why there were so few protons relative to photons, the question was asked the other way. Why are there so many photons relative to the number of protons? And the idea was that there must have been something in the physics which just proliferated huge numbers of photons and increased the entropy of the universe. Where did all this entropy come from? So it was thought that what we needed was an explanation of some kind of process which just created wholesale enormous amounts of entropy out of organized energy, out of energy which was organized. Eventually, the question got turned around the other way. There's a certain amount of entropy in the world. That entropy has not changed very much, but somehow the protons and antiprotons disappeared, became photons, and left over only this very, very small fraction. So the emphasis changed from trying to explain the production of entropy, the production of photons from nothing, basically, to the question of why in the early universe the imbalance between particles and antiparticles was so small. Nobody ever found a way to create all that entropy through the expansion of the universe. All that entropy means this very large number of photons. So nobody believes now that the problem is how do you create entropy. Everybody believes the problem is, the problem at the moment is verifying in either laboratory or otherwise that there's a violation of baryon number. And that'll probably happen sooner or later. In these big experiments involving these huge quantities of water, wait 100 years and a proton might decay. That's the sort of estimate that's out there now. Wait 100 years and one proton will decay.
Make sure you're looking at that time.
Yeah, that's the question. I mean, you got to run these experiments for a long period of time, and who's going to pay for them? Right.
Tough on the graduate students.
What happens if it decays while the graduate student is asleep? Okay. No other questions? Good. Yeah.
Neutrons will decay into a proton electron.
Right. And neutrino. And neutrino, antineutrino.
I'm wondering how the neutrons persisted beyond the 15-minute half-life. Is there any left in the universe after that time?
Right.
Cool.
A free neutron will decay in 12 minutes. I forget what the number is, 12 minutes, something like that. Free neutron. A neutron, incidentally, also has baryon number, same as a proton. So here's an example of a process which does not violate baryon number. It's called beta decay. a neutron becomes a proton, an electron, E minus. So far, it's a perfectly good process. An electrically neutral particle becomes a plus charge and a minus charge. And also at the same time, an antineutrino is emitted. That, for technical reasons, the antineutrino has to be there. This is a process, and it does happen. All neutrons, sooner or later, decay like this. And they last about 12 minutes now before they decay. That's the half-life. Maybe it's 15. I remember 12. But it's an interesting question why they last so long. Elementary particle processes are usually measured in very, very small time periods. Why does the neutron last so long? And the answer is a combination of answers, but one of the elements that goes in is that the sum of the mass of the proton, the positron, and the neutrino is almost exactly or very close to the mass of the neutron. So that means if these particles were a little bit heavier, there wouldn't be enough energy for the neutron to decay. So if the proton was just a little tiny bit heavier, the neutron could not decay at all because there wouldn't be enough energy for it to make a proton, an electron, and a neutrino. It just so happens that the neutron is almost equal, is only a tiny bit heavier than the proton, and just a teeny, teeny bit heavier than the proton plus the electron. So there isn't much energy there. And for that reason, the process takes a long time to happen. But yes, the neutron decays, and that's a neutron, a free neutron. Now, if a neutron is bound in a nucleus, it may have some binding energy. Let's put it into a nucleus with some protons. Let's say with a proton. Then there's some binding energy. There's some nuclear binding energy, and the energy of the neutron and the proton is not the sum, or is not the mass is not the sum of the neutron plus the proton, but it's the neutron plus the proton minus the binding energy. Right? Here you might say, why doesn't this happen? The proton just go off and the neutron decay. And the answer is that there wasn't enough energy to begin with, because there was all of this negative binding energy, which was enough. The binding energy of nuclei is very small. It's not very big. But the available energy was small to begin with. So the neutron, when it binds to the proton, becomes stable because it just doesn't have enough energy to decay. So, yeah.
Are neutrons created, or the number of neutrons in the universe constantly decreasing?
Decreasing? Yeah, it's probably constantly decreasing. Yeah, if a neutron gets knocked out of a nucleus somehow, then it will decay. So, for example, cosmic rays don't have neutrons in them. Why don't they have neutrons in them? Because the neutron decays before. What does it become? It becomes a proton and an electron and so forth. So, yeah, I guess it's probably fair to say the number of neutrons is decreasing.
Where do they come from?
Nuclei.
But I mean, after the Big Bang.
Well, actually, I take it back. There is a source of creation of neutrons, and it's a big source of creation. It's neutron stars. Neutron stars. When a star collapses, it can become very dense and
well, hydrogen burns into helium in the sun.
Yeah. There's nuclear reactions, which there are nuclear reactions, which right. Yeah, I take it back. It's probably not true that the number of neutrons is decreasing. It's probably increasing because of what you say. Yeah. Okay, if we're finished.